Then we are ready for video 5 in thermodynamics by Lars Erik. This is about the shortcut method for estimating the saturation pressure from the reduced temperature and the eccentric factor. We define the reduced temperature at temperature divided by the critical temperature, and omega, or the eccentric factor, is defined as -1 minus the logarithm of PR saturation at reduced temperature 0.7. This is the eccentric factor. And then we base this on an equation that the logarithm to the partial pressure is minus the vaporization enthalpy divided by R and Tc of Tc of T minus Tc over Tc. This is the Clausius-Clapeyron equation with the critical temperature inserted instead of the reference temperature. And then the logarithm of the reduced saturation pressure is the vaporization enthalpy divided by RTC of 1 minus 1 over TR. Then we convert to common 10 logarithms, so that the logarithm to PR set is 1 over 2.303 delta H of vaporization over R times Tc, 1 minus 1 over TR. Or logarithm to the set is a constant A times 1 minus 1 over R. Then we assume that the vaporization entropy is constant. Then, from definition of the eccentric factor, the logarithm of PR set at TR.7 is minus omega plus 1 and this should again be with this one inserted A minus 1 over 0.7. The reduced temperature should be 0.7 or minus 3 over 7 times 8. And then we have a value for A as a function of the eccentric factor. And the result is that the log 10 of the R sat is approximately 7 over 3 omega plus 1 times 1 minus T over T reduced. And this is the shortcut equation. So what I have done is to deduce this one. It is a method for estimating the saturation pressure from the reduced temperature and omega, and these values are available for almost any components, and it is based on the definition of the eccentric factor, and it is based on the Clausius-Clapeyron equation. And then we have this equation. So if we know omega, we know the reduced temperature, then we are able to make an estimation of the saturation pressure. That is the end of video 5.